let's get started. So, what am I going to talk about today? I'm going to talk about a few patterns for more resilient software design. The idea of that talk is to give you a brief motivation why it makes sense to build more robustness, resilience, fault tolerance, you name it, into your software application. There's a difference between all these terms, just to be clear, but that's a story for another discussion. So a topic for another discussion. That it's important, and then afterwards, I'm going to show you that is not so hard to start with. So we will build a little beginner's toolbox with patterns in there that you all know and know how to handle and so on, that just after the session, you could start improving your applications in your company or wherever you are. So, and that's the goal of my talk. Let's move on here. So my name is Uwe Friedrichsen. I work for a company called Codecentric, my current employer, and on the internet, most social media, you usually find me with my handle UFried, for instance, on Twitter, on SpeakerDeck, where you also can download the slides, or on my private website, where I also have a blog and some other places. Mentioning the slides that you can download, as we have about 45 minutes plus Q&A. I will have to cut a few corners because the slides were made for a 1-hour talk, and so I have to skip a few things, but if you download the slides, you can look them up later. Okay, so much up front. Then let's dive into the topic. And we need more resilience, which raises the first question. What is this resilient thing anyway? Because, well, it's a little bit fuzzy term. And so you maybe pick a dictionary and look it up, and you find something like, hey, it's the ability to recover quickly from illness, change, or misfortune, or the property of material that enables it to resume to its original shape or position after being bent, stretched, or compressed. So elasticity. Think about that for a moment. Well, yeah, after 2 years of COVID, probably this sounds like a very desirable property for me as a person, but what the heck does that have to do with IT systems? And so I try to translate that quite simplistically to IT systems. And the definition that I came up with, so quite simple definition is, I say, resilience for IT systems means the ability of a system to handle unexpected situations without the user noticing it, in the best case, or with a graceful degradation of service and a quick recovery to normal operations mode if it doesn't work so well. So we could debate this definition for hours, and that's okay, but it's a good starting point. And if you read through that, you might think for yourself, it sounds a lot like availability and reliability stuff. And yeah, you're right. And this often raises the question, so can't we leave that to the ops folks as we did it in the past? I mean, in the past, whenever somebody said, yeah, we need high availability, then we moved on and say, yeah, hey, ops people, do something about that. Create some high availability cluster, software, hardware, whatever, you name it. We don't care. We just do our business logic, and you care about all this availability and reliability. And we still see that quite often these days, implicitly or explicitly. So either people asking this question, or implicitly they keeping on programming as they always did and not caring about it. The problem is, it doesn't work that easy anymore. We can't leave it just to ops people. Which raises the next question. Why? Well, for a single monolithic and isolated system, all that might work, leaving it to ops. So as we had it in the past, so quite monolithic big systems, not talking to any other systems, or if they were talking to some other systems just via batch files or anything like that. That's okay. Our biggest concern was that the hardware, the infrastructure would fail, and so we could leave it to ops. But these days, almost every system is a distributed system. And we don't have to go to microservice for that. Most likely also the system that you create is or the system landscape you're working in is a distributed system landscape. I mean, your application most likely will talk to a lot of other systems via remote communication, the directory server, your database, this other service, whatever, you name it. There's a lot of things that probably need to be up and running and communicating that your application is functional. And distributed systems are different. So let's talk about distributed systems for a minute or two. And the background image is deliberately chosen. So distributed system in a nutshell. The shortest definition I know about distributed systems is one that Werner Vogels, CTO of Amazon, once did. He said, everything fails all the time. And that's not because the folks at Amazon are particularly dumb or anything. Quite the contrary, they are really good regarding distributed systems, but distributed systems exhibit some failure modes that you simply don't have inside a process boundary. For instance, crash failure. So the other system that you're just calling is gone, or mission failure. So sometimes it works, sometimes it doesn't. Timing failure, it works, but it takes too long. So you have someone out there waiting for your response, and the other system that you call for completing your request takes too long to answer. Or response failure, other system answers, but in some way the answer doesn't match your system, so it doesn't fit in some way. Eventually, consistency is one of the reasons other systems are also around there. And then Byzantine failures, system went amok. We won't dive any deeper into Byzantine failures in this talk, but that's a specific thing. And most people say, yeah, well, that's okay. Basically, I got it. But it's quite hard to connect that to your daily work. And so if you dig one level deeper, these failures lead to some very strange effects. For instance, that, yeah, you just lose the message, either your request or the response, or it's incomplete or distorted, or you get it twice, or it takes too long. We talked about that, which leads to out of order message arrival, like your withdrawal request arrives before the deposit request. Even if you look into the timestamps in the messages and the requests, you figure out that the deposit came before the withdrawal, but somehow the infrastructure reordered them, and well, can the application handle that? Or partial out of sync local memories, which means that all your that each node in your system landscape has its own concept of what's the global state, and they can be different, and you have to deal with those situations. And all these things can lead to effects that are very hard to handle in distributed systems, which are no-brainers inside a process boundary. For instance, time and ordering happens before is a no-brainer inside a process boundary, unless you screw up thread handling, but there are good ways around that. We all know that, but usually happens before. What happens before the other thing? We know it inside a process boundary. Across process boundaries, it can be an unsolvable problem or consensus. What's the current value of variable X? I mean, we wouldn't even think about this question inside a process boundary, but across process boundaries can be unsolvable problems, and so on. So to wrap that part up, distributed systems means that you get some non-deterministic behavior which affects you in terms of execution completeness, message ordering, communication timings, and some other things. And we can't just capture them on the infrastructure level and deal with them, they will hit us at the application level. So we will need to be aware of these effects and know how to deal with them if they happen, to really create a reliable and highly available application. And that should be the motivation. 10 minutes long enough for that. And let's assume you buy that and say, yeah, well, that's cool. I understand that. But how do I start? I mean, it's okay if you sit there and say, no, not completely convinced, but then please do me a favor and dive a little bit deeper into distributed systems and their effects, and you will then quite quickly realize why it's important and that the infrastructure cannot hide everything. Okay, let's just say, assume that you say, okay, I want to do that. Let's get started. And how can we start? And if we look into resilience and resilience engineering and resilience software design, it's a huge topic. And many of the aspects don't have to do anything with software development, to be quite clear. But let's go into one corner of the whole domain, of the whole field, and start quite simple. I mean, simple is good because we know how to do it. And quite often, simple measures improve the situation quite a lot already. So let's create our starters toolkit. First toolbox. And put a few patterns in there that all of you know how to implement and can start with that tomorrow, maybe, or even this afternoon. Here's the toolbox. It's still empty. And where to start best? My suggestion would be to start with accessing other systems. So we call another system. What could go wrong there? How can we improve the situation? So let's create some room for accessing other systems. And here's a little example. As I'm often on conferences where people say, hey, do we have code examples in Java or in C# or in JavaScript and so on? And so let's be fair to all of them. I use Python. So, but basically it reads almost the same in all these languages with the current libraries of today. And here it's Python URL lib3. And I create a simple example here is I create an HTTP client. It's called Pool Manager, and there's a URL, and I create an instance of that HTTP client, and I send a request out there called a request method, send a GET request to the URL, and then I get a response, and the response has some methods and some properties, for instance, data, which gives me the payload and so on, or headers, which gives me the header fields, list of header fields, or status, which gives me the HTTP status, and so on. Well, easy enough. And looks familiar no matter what programming language you probably use. And basically, we find code like that surprisingly often in our production systems. So if we have a code like that, an example, the first question is, what could go wrong? And I just used the failure types that we just seen before. So for instance, I don't get a response, so the other system probably crashed. Or I don't get a reliable response. Sometimes I get one, sometimes I don't get one. Or get a slow response, it simply takes too long. Or I get the wrong response. So I get the response, but I cannot process that response because it doesn't work for me. So invalid or whatever. And now knowing what could go wrong, the next question is, how can I detect that? So before handling, I have to detect it. And here come the first patterns. And the first pattern that I want to introduce is simply error checking. So for figuring out if you've got a brittle connection or a crashed peer, quite often you simply get an IO exception or something like that immediately back, which says, well, something went wrong. And that's a very, very basic pattern in the domain of fault tolerance and resilience. And still, we see it quite rarely implemented well, to be clear. So, I mean, we know how to deal with that. I mean, in Java and C++, we have, and also in C#, we have exceptions. In C, we have the return code checking. In Go, we go with an extra return value, an error return value, and so on. And still, we see it too rarely. And I think the reason for that is twofold. One thing is implementing good error checking makes the code harder to read. I mean, was this wonderful, nice code that we had before when we just implement our business logic, and then we added error checking and it sucks. It just looks ugly. Ugh, yikes. And the other thing is, well, I catch this exception and then what should I implement? What's the logic to implement? We don't know. And I come back to that question later in another pattern. So error checking. The next thing, which we can use for many failure types, is checking for timeouts. Similar story, different effect. So we don't get an immediate response that something went wrong. We get a response. We don't get a response in time. And so as we want to give our response in time, we have to check that. So usually we have to create in some way some other thread which executes the downstream call, and we have to monitor that. And if it takes too long, yeah, we have to interrupt that and do something else. And it's very essential. And we get a quite good library support in most programming languages. And we always need that if we have synchronous communication styles like HTTP and all these things. And often it's neglected. People say, yeah, but we're doing events, sending events through the event bus or messaging and so on. So we don't need that, which is not true, to be clear, because you have to distinguish the functional communication style and the technical communication style. On a functional level, there might be some requester on top of you that called you, which said, well, I expect a response within, say, 500 milliseconds or something like that. And even if you use messages or events or anything like that, it doesn't make a difference, because if that caller doesn't get his or her answer or its answer, if it's a system, within 500 milliseconds, well, they will go away. You violated your SLA. So you also might need to check for timeouts, even if you're using asynchronous communication on a technical level, because it's important what kind of communication and expectation you have on the functional, on the business level. So have to implement that. As I said, good library support again. For reasons of time, I will skip that one and move on to that one. So just to illustrate how that feels and how simple it actually is to add these patterns to your code. Here's the code we had. And now let's try to implement that with standard library means, so basic standard library means. And yeah, it's a bit longer, but it's not that hard to understand. I mean, there are some imports, and then we have your URL. Then we wrapped the actual request in this get URL function. Then we instantiate the HTTP client again, and then we have a little worker, a thread pool executor. So it's better than firing up threads on your own. And so we create another thread with that one, and then we submit this request, this remote call to the new thread that we just created, and we get back a future, and then we can do the typical try catch, or in Python try except block. So we can try to access the result of the future, and this result method has a timeout parameter that we can use. So okay, we wait for 500 milliseconds, and if it takes too long, we get a timeout error. Yeah, here we got it, and we can respond to it. And otherwise we get an HTTP error. So that's the basic exception, the core exception that the URL lib3 throws. Basically, there are more than 30 sub-exceptions where we could fine-grain figure out what went wrong. But here, for sake of illustration, I just took the top-level exception here from URL lib3. And yeah, something else went wrong. And we got it. I mean, it's a few lines of codes, but it's quite straightforward. And it's a lot better than the thing we had before. And then what we also can do is we can read the documentation of the library that we use, which is often a good idea because they often also already give us some means. And I did that, and surprise, I figured out that the request method of that pool manager of that HTTP client has an optional parameter, timeout. Hey, here we are. And now the code is a lot shorter again. So I have a simple try except or try catch block. So try, we send out the request. I get back an exception if something went wrong, including if I ran into a timeout. Again, looking for the right sub-exception, we would immediately figure that out. But for here, that's good enough. And then otherwise, it's okay. Well, you can implement that straightforward. Okay, moving on. And what are we going to do if we get, so how can we detect a wrong response? And again, that's very straightforward. It's response value checking. So yeah, it sounds so obvious and I see it so rarely in the code. Therefore, I really mentioned that. I mean, we have to check that. I cannot count the number of times I have seen null pointer exceptions in some production logs because people just went down to the database, read some data, and then immediately started processing the data, not checking if any of the values were null. Bam, null pointer exception request was gone. Unfortunately, the request was that some of your customers wanted to buy something, and the request just vanished into the nirvana of your production log, which is not good. So we have to check what we get back and if it makes sense or not. So yeah, do it. And we have quite good library support for that. They cannot check everything. So sometimes you have to add something on your own. And also what can make sense in a language like Java, for instance, which is object-oriented in its core, considering specific data types so that you don't get back a string, but that you get back a phone number, for instance, that you create a data type for phone number. And then in the constructor, you can check if that's a valid phone number or not, what you got, and so on. Okay, and by the way, it also makes the signatures better readable. Now we detected all the stuff. Someone's unmuted. So someone's unmuted their microphone. Maybe technically, maybe they can mute themselves again. Oh, yeah, thanks a lot. Okay. Now we detected that something went wrong. What can we do about that? Let's start without adding redundancy, so multiple nodes. And the first thing that comes to mind is immediately, let's retry it. Maybe it's just a transient problem and it goes away if we retry. We know that from the websites. We try to load a website, a page, and it hangs, and we click retry, and here it is. It works immediately. So it's a very basic pattern and we should try that. And that's quite straightforward to use that. The point is that we shouldn't retry too often. So sometimes I see things like retrying 10 times, which doesn't make any sense usually. So the rule of thumb is usually just retry one time in a production scenario if you're not trying to create a connection, but if you really try to get something. Or if you don't have a timeout situation and you have the time, maybe you can use exponential backup, so waiting longer and longer between different retries and then retry it several times. But either one time, if you're in a timeout situation, so constrained time period, and if it doesn't work, try something else, or the exponential backup. And again, quite some library support available for that. Now we tried retry. Here's another one that I'm going to skip. You can read it up in the slides. There's also a paper referenced, which is quite interesting if you want to go into that one. It's a quite sophisticated retry variant that Google implemented, basically. That's described in the paper. But it requires some kind of redundancy, so multiple nodes. But you did the retry and didn't work. So what can we do then? And then what we hear quite often is, let's try caching. So let's reuse some response from some prior calls or have a data cache or whatever. And that's a good idea to bridge some temporary unavailability of resources. But be careful. If you use this caching all over the place, it requires memories, it requires energy, it requires other resources, it requires network bandwidth and so on, which can cost a lot of money and even impede your other production environment. Because if you send a lot of data around, you might get a network saturation or a situation or something like that, which you don't want. And you have the stale data problem, that these caches become stale, that the data in there becomes old, obsolete, and then you have this out of sync partial memory and all these things, and that you need to deal with. So be aware what you're doing. It's a good pattern, but use it with a little bit of caution. If you use it, quite good tool library support available. And if caching is not the solution, well, then the other thing is maybe looking for the fallback pattern, which is the generalized variant of caching. Basically, I mean, caching is just one implementation of fallback, because fallback simply is a very general or generic pattern which just says, what's your plan B if plan A fails? So make sure that if your request fails, if your retry fails, what are you going to do then? So have a plan for that. And we often see the fail silently, deliberately or not deliberately, so that you simply ignore the request and then move on, which sometimes a good idea, quite often it's not, or a default value, or if I don't get a response from there, I can use a default value or something else. And the important thing here is, and that's also if we remember the error checking and also the timeout pattern, why many people don't implement them. They don't know what to implement then if all this stuff fails. So if you run into a timeout or get an error and you retry and you still get an error, and now what? And that fallback is a business decision, because it's depending on the criticality of that request, of that use case that you're just implementing, that user interaction. It might be sufficient to silently ignore it or use a default value. Or it might be okay to send back an answer to the user, well, come back in 5 minutes and retry again then, for the 503 in HTTP terms. Or in some other situations, maybe it's the buy now button of an e-commerce site. You want to make sure that you capture that, and you will invest a lot of money. I mean, Amazon even created a whole database from scratch for making sure that they will capture everything, as long as one node of how many, whatever they had, of the database is up, that they capture everything that goes into the shopping cart, because everything that goes into the shopping cart, every euro that goes in there is so many cents of revenue. They knew that, and it was the most important thing for them. So they invested hundreds of person years for that. And course, there's a long range and we're not Amazon, but that's a business decision. So your product manager needs to say, okay, that's a very valuable thing for me. It's okay if you put a lot of effort into mitigating or handling the situation, or say, well, not that important. Send out an error message to the user, that's fine. You have to ask them. Without asking them, you will never know what to implement if you catch the IO exception or the timeout exception. Okay, let's add the retry and the fallback to our code. Up to here, it looked like that. And again, let's go for retry and fallback with standard library means. Second, please. Okay, and gets a bit longer again. So we have the HTTP client again. We wrap the whole try except block in a function now. And for convenience, we say, okay, it returns none, which is the null equivalent of Python. And if something goes wrong and otherwise, it immediately returns to payload. And then down in the bottom line, then we try to access the remote resource. So D equals get URL, HTTP, and with parameters HTTP and URL. And if it doesn't work, so if it returns a none, well, we simply do it again. And if it's still none, we execute our fallback. And in IT, we all know 42 is a good reasonable fallback for many things. So we use that one. And then we're done basically. And the idea of that is to make sure that it can be that simple. Usually you would write that in a different way, not that simple. Maybe if you have higher order function, you would wrap that in higher order function and all that stuff, which you should do. And maybe also implement some higher exponential backup or options and so on. But this is a lot better than the thing we had before. And it's that simple. So it doesn't need to be fancy or complicated or anything. It can be that simple. So, but we also can read the library documentation and figure out that, oh, request has another optional parameter, retries, that we can add. And so we did. So can be easier. Reading documentation often is a good idea. And last thing here, before moving on, is then what can we do if we have redundancy? Well, sure, failover, which means that we fail over to another node, does the same thing. And that's quite good if all the other things do not work or take too long. And we have a lot of variants available. Also on the infrastructure level, we have great support for that. Because, I mean, load balancers are there, Kubernetes does that for us, and so on. So it's all there. The only thing you should keep in mind is it costs money. If you have 3 replicas running just for the situation that maybe one of the replicas doesn't answer quick enough, you pay 3 times the money. You waste 3 times the resources. And so make sure that it's really that important before you do that. I mean, it's very easy to write replica colon, so replicas equal to 3 into your deployment descriptor of Kubernetes or something like that, but mind the consequences of that. So make sure that it's really worth the effort. And with the response value checking, yeah, there's not a pattern. It depends. So maybe we can ignore the value. Maybe there's a default value we can use. Maybe there's nothing we can do about that. So we have to return an error or whatever. I just want to remind you of Postel's law. John Postel, Internet Pioneer, wrote the original TCP specification in 1980. And in there he wrote something like, be conservative in what you do and be liberal in what you accept from others. Or often reworded as, be conservative in what you send and be liberal in what you accept. So what he meant is, if you send out anything, try to stick to the protocol as good as possible. But if someone else sends something to you and you can make sense of that, please do it. don't go and say, no, that's not exactly working with the specification, and therefore I'm not going to accept that. I mean, a great implementation of these things are web browsers. It's unbelievable what kind of HTML they are still able to make sense of and how broken that stuff can be. We don't have to go that far. And we also have to make sure that we don't fall for security also. But maybe if a phone number comes along, we're not going to accept only numbers only. Maybe the plus in the front is okay. Maybe you can also add parentheses or slash or a hyphen or blank in there. And yeah, it's more effort to write a parser like that, but it makes your system a lot more robust in the end. And with robustness also comes some kind of resilience of the system. So try to keep that in mind when writing the next parser for your APIs. So much about downstream. Let's briefly touch upstream. So recalled by other systems. And yeah, let's have a little example here again. Again, Python, I use Fast API as HTTP server here. But in the end, it almost looks the same as some Spring Boot code or something like that. So you can read that immediately. And yeah, it's we instantiate the the server, and then we have an annotation, a routing annotation, which says, yeah, the get for the URL square with a number parameter is routed to that read square function, and then we convert the parameter into an integer, and yeah, and then we return the square of that integer. And yeah, it's quite straightforward. And if I would ask anyone what could go wrong in here, all hands would go up and would say, yeah, we're at the number conversion. And you're absolutely right, of course. Still, surprisingly often you see that even in production systems. So yeah, request parameters are wrong. And the other situation I want to talk about for a second is then looking for overload. And so if you're called too often, if you receive more requests than you can process, what you can do then. And the first thing, how can we detect wrong request? Yeah, it's the same thing as the response value checking. So even the slide is the same, actually. And just to be clear, if everyone would get their request parameter checking right, 95% of all security vulnerabilities would be gone instantaneously. So it makes a lot of sense to do good request parameter checking and implement that. So let's add it. And here's the code. And let's assume that there's a business requirement that this number must be an integer between 0 excluded and 100 excluded. So every number from 1 to 99 is okay. And this time I immediately read the documentation of the library and hey, surprise, there's something. So we can simply say, okay, number must be an integer. And this path expression behind it, as it is default value, means basically reads away. So the 3 points mean there's no default value, and then GT is greater than 0 and less than 100. And we're basically done. And luckily, what the library provided was good enough for us. Okay, quite straightforward. And the other thing, how can we detect overload situation? And in general, yeah, we need some kind of monitoring. We always need some kind of monitoring when running distributed systems, and we even should have it for monoliths, but we absolutely need to have it. And there's a lot of good support available. The only thing you have to keep in mind is that quite often you have to support it from the application level for getting the best performance. For instance, if you have a server that often works with a worker thread pool, and then in front of that worker thread pool, you have a request queue. And if that request queue becomes longer, that's a good indicator that you run into an overload situation. And so, but the monitoring solution usually cannot immediately figure out this request queue and how long it is. And so you have to provide some metrics for the monitoring solutions. So yeah, we need monitoring. And what can we do if we figure it out? Yeah, for request parameter checking, it's obvious. It's the same thing as with response value checking. And for monitoring, depends if we have redundancy or not. Without redundancy, we need some kind of load shedding. So shed the load. We usually know it as rate limiting or like that. So most API gateways have built that in, and some other service meshes, I think, also provide options like that, and so on, that we can say maximum of 100 requests reaches per second reaches that endpoint over there, that service over here that we just created. And that's okay. And let's skip the rest of that for the sake of the time. So we have to shed some requests. And if we have redundancy, yeah, we have to share the load, which we know as scaling. The name of the pattern is just differently. So we share the load. If we figure out that we cannot handle all the requests on our own, fire up another instance and share the requests. Load balancers can do that for you. You can do that statically or dynamically. I mean, most cloud environments offer auto scaling, and some service meshes also offer auto scaling. Oh, that's quite good support available. Okay, so we are quite advanced in time. So I will skip most of them except for one, for the complementing patterns. So let's create some place here and mention monitoring once again. Only idempotency I want to mention briefly, because many of these things only work properly if you have implemented idempotent call. Idempotency basically means that you can repeat the call without and always get the same response and do not trigger any accumulating side effects. And so that's important, because if, for instance, with a non-idempotent situation would be something like that you have, sorry, just lost my track. Non-idempotent call would be something like increase counter. And increase counter is non-idempotent because it makes a difference if you call it 1 time, 2 times, or 5 times. Set counter to 4 is idempotent, and then it's straightforward, basically. So you can call it 1 time, 2 times, 5 times, or 100 times, and it works. And you can only do a retry if your call, if the other side is idempotent. Otherwise, you would need to figure out the internal state of the other side, if it's safe to do a retry and call it again, and so on. It makes it hard. So you have to implement that. So keep idempotency in mind. There's a lot of good documentation around there, how to implement that. Let's skip the other ones and have, as the last thing is question. What can we delegate to the infrastructure? Well, I will keep that short. So if we look for instance, error checking, timeout, retry, and so on, basically all these things, yeah, there's some support on the infrastructure level, but it's quite coarse-grained. So it simply says, yeah, well, you can set a timeout for accessing that other service, but you cannot specify it for this method and that method and that method. And it can make a difference. If it's okay for you, it's great, use it. If it's not okay for you, so if you need it more specified, say, okay, this method must return in 200 milliseconds, but for the other ones, 2 seconds is fine. You have to set that on the application level. Caching, yeah, a lot of caching frameworks and stuff is around, but you have to implement logic on your own. Fallback is pure business logic. Failover, good support on the infrastructure level, can use that. Response value checking, request parameter checking, pure business logic. Monitoring, you get quite good support, but you have to augment that on the application level usually. Custom response is, of course, business logic. Shed load and share load. It's great on the business level. It's great on the infrastructure level, supports you well. And the other ones we didn't discuss anyway. So, and if you look at that image, say, well, wrap up. That's still a lot to implement, isn't it? So I'm not quite happy about that. So I have to care what about these things. But the question is, what's the alternative? To be honest, I mean, should we let the application crash whenever something goes wrong just because it's easier? I mean, the point is, the question is no longer if something will go wrong. The only question is when and how bad. And it will go wrong whenever you have the biggest load, the most successful day of the year on your systems. That's when it will go wrong. So look for library and framework support. So you get a lot of support on the library and framework side, not on the infrastructure side, but please do the work because everyone loves resilient applications. The users love them. If that's nicely available, reliable, responds quickly, and so on. It's cool. Your ops team loves you for that because they have a much better job than they had before. Your product managers love you because you don't get that much fire from other sides, how bad the application would be, and. So let's come to an end. Wrapping up. Before maybe going for one or two questions, I will answer the other ones then offline, basically. I'm looking at the watch. We've seen distribution makes resilient software design mandatory. So it will hit us on the application level. We have to take care about that on the application level. We created a little starters toolbox that you can easily use. Again, my intention was to make clear that this is not big magic. That is something that you can start with immediately. And I hope I was able to bring that idea across. Infrastructure gives us quite good support in some places. Use that, but consider the limitations. And of course, look for library and framework support. Because again, everyone loves resilient applications. And if you download the slides, you will find some more readings and so on. And yeah, that's what I had for you. And now I will briefly look into the chat. See. What's Byzantine? Byzantine is when the system runs amok. Basically, it's a failure mode. It's called after the Byzantine generals. The Byzantine generals problem written back then in the early 80s by Leslie Lamport, who described us if some party does a wrong play, a foul play, how can we figure that out? And so basically it means you cannot predict anymore what's going on. So what's the name of the DB Amazon created? That's the original Amazon Dynamo, which they used as the basis later on for the DynamoDB, which you can instantiate on AWS. Exactly. So it's not the DynamoDB as someone here, as Eduardo wrote. It's the original one was Amazon Dynamo. There's also a scientific paper for that one. And then you can go. So do you also check for supernumerous arguments? We can check for that, but we can be tolerant about that. So if you have too many arguments and we don't need them, we might ignore them, which makes our system more robust for upgrades and updates so that you have fluent updates and so on. Sharing the slides. The slides are already available on the speaker deck account, but I will also send out a tweet for that. Is the use of functional programming with event stream systems a good answer for some of the problems? It can be useful. It can be really useful, functional programming. Especially it can help you to write better abstractions for some common situations that you can reuse in many places and so on. So functional programming is always a good idea, not only here. Okay, it's 9:51. So sorry for being a little bit fast. I told you it was a longer one. I hope I got the idea across. And then if there are no other questions, thanks a lot for your time and your patience.